Well, hello, my name is Emmanuel. I'm an electrical engineer from Costa Rica and currently an Erasmus master student in imaging and light for extended reality. And today I'm going to present you my work on deep color calibration. So first of all, I'd like to introduce what is color calibration and the problem that we're trying to solve with this approach. Color calibration is a method through which we can achieve consistent color appearance among images. So it works pretty much as follows. We will have a reference color checker with a series of patches. We know exactly how each patch should look. And what we do is we have an image with a color checker in it, and we perform a series of color transformations in that image so that each color checker matches the reference color checker. This brings up a very evident problem, and it is that most images don't have a color checker in them. So in order to solve this issue, we came up with a proposition, and it was to use deep learning to infer the color information from an image that otherwise would be given by the color checker and calibrate the image accordingly. Okay, so we did the following. We had a series of images with color checkers in them. We proceeded to color calibrate those images using the color checker. And afterwards, we removed the color checker both from the non-calibrated and the calibrated images. And we, with this, we generated a series of input-output image pairs that we used to fit a neural network to teach it to calibrate images. As for the data, we counted with 3 data sets, 2 of which consisted of outdoor images with color checkers in them, and 1 with that consisted of indoor laboratory images. And yes, as for the architecture, since it was just a proof of concept, we tried to keep it as simple as possible. So we grabbed a fairly simple convolutional denoising autoencoder architecture with pretty much default hyperparameters and with a mean squared error as the loss function, and proceeded to run tests with that architecture. For the training, due to timing constraints, we just had the time to perform 3 experiments. The ones that are presented in this slide. As for the one-pass training, this means that we directly train the autoencoder with the non-calibrated images at the input and the calibrated images at the output. For the 2-pass training, this means that first we taught the autoencoder to reproduce the exact same image at the input and at the output. So we trained the autoencoder first feeding the same image at the input and at the output. And for the second pass, we trained the autoencoder with the non-calibrated images at the input and the calibrated images at the output. With small data set, that refers that we were just using the first data set of 568 images. And for the large data set, it means that we were using all the available images. With each of these experiments, we see an increase in the performance of the model, though it was very little, but it was still there. As for the results, qualitatively, we could tell that the model did a pretty good job, especially on this type of images, outdoor images with a lot of grass, a lot of trees in them. It did a fairly good job on the image calibration task, so that was great. However, it was not perfect. In fact, it was far from perfect. It had several issues with images with yellowish tones, and this was particularly noticeable in images with people in them, since it would calibrate the images so that the people in them would look pale, which is an undesired result. and same thing for images with sand or wood or gel materials in general. And for a lot of images, it is just as this one presented in this slide. And although we can see that it did not achieve a perfect calibration, it managed to balance the colors from the scene pretty well. And that was the case for most of the images. In order to have a more quantitative analysis on the results, we used a delta E color difference function per pixel. We're comparing the expected output and the output of the network. And though the average mean difference was fairly high, most likely due to the presence of outliers at the borders of the images, the median difference between the expected and the actual output was very decent, especially considering that we did little to no optimization whatsoever regarding the architecture or hyperparameters or training, and that we had also several hardware limitations that didn't allow us to run better experiments. So that brings, well, that creates a lot of room for improvement. There are several things that will definitely improve the performance of the model. The main thing that we believe that would improve the performance of the model would be to utilize a custom the color difference based loss function. Since we were using the mean squared error as the loss function, which would basically correspond to the Euclidean difference between the expected and the actual output colors of the pixels. And as we know, Euclidean distance is not the best measurement for color difference, especially because it doesn't account for human perception, whereas other color difference loss functions do. Another improvement would be to utilize a more complex model. So, for example, a variational autoencoder or another more complex generative architectures, such as pix-to-pix architecture or a generative adversarial network. Although we don't know if it would improve the results, it would be something that it may be worth trying. And lastly, it will be also interesting to try and perform a color transformation data augmentation on the dataset to see if that also improves the results. And yes, that will be pretty much it. Thank you very much for your attention.